If you're doing any kind of electrical work, you need to take measurements. Just like a carpenter would use a tape measure to measure things, you'll be using a meter to take voltage or amperage readings, or perhaps to measure resistance. I have a selection of meters here. We have some digital meters. I also have a couple of analog meters. All of these meters have batteries in them. The digital meters use the batteries all the time. The analog meters only use the batteries when you're measuring resistance. When you're measuring voltage or current, they actually obtain the power to drive the needle from the circuit that you're measuring. We'll be doing some simple measurements today, measuring battery voltage and current in a circuit, measuring some resistance, and then I'll also point out some ways that by adding the meter to the circuit, you'll actually affect the circuit. We'll just pick a couple of these meters and take our readings with those, but I just want you to be aware that there's several different styles of meters. There's obvious differences between the analog and the digital, of course, but even in the digital meters, there's auto-ranging and manual ranging meters. And then also the connections to the meters, of course, typically there are probes that you'll use to touch into the circuit. Also, I quite often prefer to use alligator clips, so I've equipped several of my meters with alligator clips on the end of the test leads rather than the test probes. We'll start first by looking at this meter. This is an auto-ranging meter. The selector knob here, you choose DC volts, AC volts, resistance, diode test. It is not auto-ranging on the amperage scale, so you choose your scale and connect the test leads to your circuit. Now when you're on the amperage scales, you must unplug the positive probe and connect it to either this connection or this connection. This would be for 4 or 400 milliamps, and connect over here for the 20 amp scale. It's not uncommon for the meters, for the higher amperage ratings, for you to have to move one of the leads. Not all the meters work the same, so be sure to check your instruction manual. As I mentioned, this is an auto-ranging meter, has a very high input impedance, makes the meter very sensitive, and you'll know that we're indicating some voltage. And over here's a little icon you probably can't read, it says millivolts. We're actually picking up voltage, just like static electricity you get from dragging your feet across the carpet on the probes right now, even though they're not connected to anything. If I touch the probes together, the meter will settle out at 0 volts. So we'll move the meter up a little bit, and I'll take a 9-volt battery, and we'll connect that up and just take a voltage reading here. Just take this 9-volt battery and touch the probes to the battery, and it should read just over 9 volts, which is typical for a 9-volt battery. I've got 9.60 or 9.61 volts. Okay, and if I were to take something like a single flashlight cell and touch the probes across this flashlight cell, it should read just over 1.5 volts. We got 1.623. Okay, and if I were to take 2 flashlight cells and put them in series, I'd get double that voltage. When you put cells in series, they always add. Oops, if I can get them to sit still. .248. And this 9-volt battery actually has 6 small cells inside of it. So you get 6 times 1.5 roughly, which is 9 volts, the nominal voltage of the battery. This next meter here, also a digital meter. Turn it on. This one is manual ranging. I select my function with the lower selector. I've got DC volts, AC volts, diode check, resistance, DC milliamps, AC milliamps. And then on the upper selector knob, I choose the 3-volt scale, 30-volt scale, 300-volt scale, etc. I have to manually set the range on this. Where on this meter, it would automatically shift the decimal point to choose the range that I want. And you'll notice when I connect it to the battery, it has to shift gears and move the decimal, and it takes a few seconds to get a reading. I touch it on here, and it actually showed overload there for a second. Did you see that? Right now it's on the millivolt scale. When I touch it on here, it shows overload until it decides what scale it needs to be on. And I'm using the manual ranging meter. it's set now on the 30 volt range, DC volts. So it has a decimal point set. I'm on a 30 volt range. When I touch it on, I get just about an instant reading because it doesn't have to do any range setting. 9.5, which is different from the other meter. Now this one's been kicked around for a while, so, well, both of them have actually. They won't always read the same thing. The accuracy, even though you have a meter that says 9.50, don't say that that's always going to be exactly 9.50. They're always going to vary some. Unless you've got one that's just been recently calibrated or it's a brand new meter, they aren't always going to be exactly the same. Most of the time, the fact that it's 9.50 or 9.52 is not going to be that important. Okay, so this one uses two different selectors, one to choose the function, one to choose the range. Then I have another meter here. This was a very inexpensive meter. I got this off eBay. It was shipped in from China for about $5. This will serve your purpose for most things. Turn it on. This one, the settings over here are DC volts, and I have different ranges, 1000 volt range, 200 volt range, 20 volt range, 200 millivolts, which is 2 volts, or 2000 millivolts rather, or 200 millivolts is the lowest range. And then down here are the ohms range for measuring resistance or continuity, diode test, transistor gain. There's a little socket you can connect a small signal transistor to. It'll test that. 10 amp DC range. And then over here, milliamps, and then AC voltage on these. So you're setting both the function and the range by the position of the selector here. So I'll set it to the 20 volt DC range and touch it on my battery, and we should get a reading about 9 volts or so. 9.60. Okay, and you'll see that we get the reading fairly quick because it doesn't have to go through the different ranges trying to find the right one, because we've got it set because we selected what range we wanted. Now on the Autoranging meter, there's a range hold button, and I can press this one until I get it on the range I want and lock it on that range, and then I'll get a quick reading out of it too. So you can override the Autoranging function. The Autoranging is handy if you're probing around in a circuit that has many different voltages over a wide range, because it'll self-adapt. But most of the time you already know what the voltage is expected to be, so you can set the meter appropriately. Okay, let's say we want to measure amperage. I'm going to make up a circuit here. I'm going to take a battery and a little light bulb. I'm going to connect that up. First we're just going to light the light bulb. That's going to be our circuit. I'm just going to use these jumper wires to connect this light bulb to a battery. It's very simple, and the light bulb lights. Yay, I made a circuit. Okay, and we'll look schematically. We just have a battery connected to a light bulb, back to the battery. I can take my voltmeter and connect it. We'll observe our polarity as we should. And I'm reading 12.93 volts across the light bulb, which would be pretty much the same thing I get if I read it right across the battery. Okay? So I can connect the meter across the battery, or I could connect the meter across the light bulb. It would be the same reading. Now if I want to find out how much current is being drawn from the battery to light the light bulb, I'll take the meter. I'm going to use a second meter because I want to do something a little different here. Turn on this meter. I'm going to set it to the 300 DC milliamp range. So I'm set up to read 300 milliamps DC. On this meter, I leave this connected where it is for DC milliamps. If I was going to be on the 10 amp DC range, I'd have to move this probe over here. As I mentioned, all meters are different, so check your instructions, but for reading DC milliamps, I leave the probe connected where it is, and you wire the ammeter in series with the bulb. Okay, so I'm going to pull off the positive terminal here, hook the meter to the battery, and then the other meter lead connects where the wire was that I took off the battery. The light comes back on, and now the current is flowing through the meter. And schematically what I'm doing here is I broke the circuit where it came off the battery, and I connected my ammeter in here. Okay, so the current comes out of the battery through the meter, through the light bulb, back to the battery. The light is lit, and my meter shows me that I'm drawing 62.4 milliamps to light the light. Okay? Now, one thing that a lot of people don't seem to take into account is that having added the meter into the circuit has affected the circuit. Because if I connect this voltmeter across the ammeter, I'm going to find that I've lost some voltage. So I'll stick this meter across the two connections of the ammeter. I see that I've dropped 127.9 millivolts. It's about 0.128 volts. It's not a lot, but there is a voltage drop being added into the circuit because of the ammeter. So right across here, I've introduced a voltage drop into my circuit, which might affect the circuit some. Now, in this particular circuit, I've dropped a little bit of voltage going to my bulb because of this. Not a lot, but a little bit. Some circuits could be affected by that. So by adding the ammeter into the circuit, I've dropped the voltage to the bulb by a very small amount. There are other cases where hooking your meter into the circuit could have an effect. Even hooking the voltmeter in can, and I'm going to demonstrate that next. You see, I have a schematic here of a battery connected through two resistors and back to the battery. If the resistors are of equal value, they would each drop half the voltage. So if I had 12 volts, each of them would drop 6 volts. If I were to connect a voltmeter across just one resistor, it would read 6 volts. And connecting across the other resistor would read 6 volts. So here I have the battery, my jumper wires, and two resistors wired in series. I realize in the picture it's going to be very small, but here's one resistor and here's the other. They're soldered together and I have my jumper wires hooked to it. So I'll take my voltmeter, and if I measure across both resistors, I'm essentially hooked across the battery, and I'm reading 12.74, 12.75, about 12.74 volts. Okay? If I connect across just one resistor, I should have half that, 6.38. If I hook across the other, I would have the same, 6.37. Okay, the resistors 6.38, 6.37. The resistors aren't perfectly balanced. There's a 5% tolerance, but we have essentially the same voltage across each resistor. Okay, which is exactly what I'd expect. Now here comes the problem. If we have a really cheap meter, like this wonderful piece of junk, the impedance of this meter is very, very low. Now, most digital meters are going to have a relatively high input impedance, like remember this one that was giving me readings when it wasn't even hooked to anything. This has a very, very low impedance. It even says right on here, you wouldn't be able to read it. This one says it's 2,000 ohms per volt. Now this other larger analog meter that I have is 50,000 ohms per volt. Alright, so let's put this one across and take some readings with it. With this one still connected, and see how much this affects the circuit. So I'll connect this meter first. We'll see how much this one drops. We're at 6.38. And we dropped to 6.36, 6.37. It hardly affected it at all. And we look on this, and again, you may have difficulty seeing this meter. But looking on the lower scale, 0, 2, 4, 6, 8, we're about 6.3. That's pretty close. Hardly affected the circuit at all. Okay, 6.36, 6.37. Take this meter off, 6.38. Hardly affected the circuit at all. Then I'll take this cheap meter, have it set, there's a 10 volt range, which would be adequate for measuring our 6 volts. When I connect this on here, we dropped down to 6.18. That had a noticeable effect. We went from 6.38 to 6.18. Now this is a fairly low impedance circuit. I'm using 1.2 k ohm resistors, 1200 ohm resistors. Now if I were to change these resistors to something much higher, I've got 6.22 volts. It should be 6.38. Just this meter is dragging it down a little bit. When I hook this cheap meter on here, it drops like a rock, 0.4. The action of connecting this meter into the circuit has disrupted the circuit so severely, we go from 6.22 to 0.4 volts in the circuit. So just connecting the voltmeter into a high impedance circuit can severely disrupt the circuit. And since I brought up resistors, let's see how to measure resistors with our meter. Set the selector switch to ohms to measure resistance. Right now the meter is showing OL, overload. The resistance between the probes is so high, because there's no connection, the meter cannot measure it. So this one's showing OL. Another type of meter would have a different indication. This one is flashing 3 at the beginning of the display because it's overloaded. Another type of meter would have a different indication. This one, if I set it on ohms with no connection between, it shows a 1 all the way to the left of the display. Where it would normally be showing zeros or some digits over here, it shows a 1 all the way to the left. Check your manual, it'll tell you what the indication would be for an overload. In that last voltage divider I was using resistors. These are marked green, blue, yellow, and if you knew the color code you'd know that's 560,000 ohms, pretty high impedance. If I hook my meter across here, I'm set on ohms, it's an auto-ranging meter, so we'll give it a second to come up with an answer. It's saying 0.569, and then there's a little M there on the end before it says ohms. 0.569 megohms, which is 568 or 569,000 ohms. Said it was 560. Okay, and we'll get another resistor here. This one is brown, red, red, 1,200 ohms, 1,206 ohms. Pretty close. Okay. If we're using a manual ranging meter, like this one, we'd set the selector on ohms and then we'd have to guess what it would be. Well, since I know this is less than 3,000, we all go for the lowest range we can, so we'll set it for the 3,000 ohm range. Connect the meter to the clips. I get 1.190K, or 1,190 ohms. Okay, so that's all there is to measuring resistors, just connect it across. Now, if you connect the leads together, 0. Well, it's blinking 1, so that'd be an ohm. Little resistance in the leads. Switch contacts might be a little dirty. On the Autoranging meter, same thing. It'll shift gears a couple of times trying to find the appropriate range. And this one beeps. I don't know if you can hear it. And it's coming up telling me it's 0.1 ohms. Okay? And it's beeping, telling me it's a very low impedance. So I have continuity between the probes. And this can also be used to test things, like if a switch is on, or say if I wanted to test this fuse. I would just hook the probes across the fuse, and right now it's showing overload, the circuit's open. If I touch it on here and the fuse is good, it would show essentially 0 ohms. It's showing me 0.2, 0.3. It's jumping around, maybe I'm not getting a real good connection on here. Yeah, 0.1. So this fuse is good. Or a switch or some other thing that I might be testing with it. So those are what you can do with the ohms setting, testing for continuity between, from one wire to another, if a switch is closed, if a fuse is good, things like that. Okay, I've built a little circuit here that slowly varies the voltage up and down, and as you can see, both meters are going down right now. This circuit varies from about 1.9 up to 5 volts. We're on our way down to about 2.5 volts mid-scale. Coming down, this is 5 volts full scale on the meter, down to 2 volts, to 1.9, now it's going to start going back up. That was 2 volts right here. And now it's starting to go back up, and it's going to get up to about full scale on the meter here, which is 5 volts, and then it's going to turn around and start going back down. And we can easily track the voltage here watching this. The digital meters update a couple times a second. It's just taking snapshots and displaying it just long enough for you to see what it is before it changes again. But if the voltage is changing rapidly, then it would just be a jumble of numbers. It would be very difficult to tell what was going on. So I'm going to speed this up a little bit, make it just a little more difficult to follow the action here. But you'll still be able to see what's going on, but it'd be a little more difficult to tell. Right now we can tell that it's the voltage just gently going up and down and up and down. But now I'm going to pick up the speed a little bit. Okay, now as you can see, we're going up and down quite a bit quicker. The analog meter's keeping up fairly well, but we don't quite get down to 2 and we don't get quite up to 5, although the voltage is getting up to 5 and it is getting down to 2. It isn't quite getting there. And since this is just taking snapshots, we saw it got down to 1.3, but we may not see it get all the way down. We may not see it get all the way up to 5, all the way down to 2 every time. Okay, it's doing pretty good. We're not quite seeing it on the analog. You know, this is mechanical. It's a little slow to respond, but we're still seeing the trend. But it's kind of hard with the numbers jumping around to really know what's going on. And then now I'm going to speed it up even more, and it's going to be almost impossible to tell what's happening. Okay, now it's going up and down a couple times a second. And you'll see by the analog meter it's pretty much paralyzed. We're just fluctuating a little bit. We don't know, well, gee, is the voltage only going up and down 0.5 volt? Is that all it's doing? No, it's really going from 2 volts up to 5 volts, or 1.9 up to 5. But look at the digital display. It's just jumping all over the place. We really have no idea what's going on. To show that the voltage is still fluctuating, I've connected an oscilloscope. I've set it up so right here, that's 0 volts, and each division, although I realize this isn't real clear, 1 volt, 2 volts, 3, 4, and 5 volts right to here. And it is going from 2 to 5 volts. It's still oscillating like it was before. It's just going so quickly, the analog meter can't possibly track that fast, and the digital's just taking samples at, several times a second, just displaying what happens to see when it takes that sample. Looking at either of these, we can't tell what's possibly going on, so obviously we need a much faster instrument. So whenever you have varying readings, neither of these instruments is going to give you any good idea. We need a much better instrument, and I'll be doing a video at some time on the oscilloscope and how to use that. You can measure voltages, look at the waveform, you can measure frequency. It's a very useful instrument. Of course, quite a bit more expensive than a meter like this, but so much more versatile. Well, I hope you found this informative. If you have any more questions, you could send me an email, and I would appreciate any feedback or questions or any videos you'd like to see from me. Please let me know. Thank you.